So this is the box girder that we'll be modeling today, and it's a very simple bridge. Basically, I wanted to highlight the construction staging of Midas Civil in this example, so I chose a relatively simple example that is simple enough to create, but at the same time you are able to understand the construction sequence or construction staging concept in Midas Civil. So this is the layout of the uh, presentation or the training session today. So I'll be starting by defining materials and sections. Then from scratch I'll start creating the geometry by creating nodes and elements, and then we'll apply time dependent material properties to it. After this I'll apply the boundary conditions and apply loading onto the structure. Now while applying the boundary conditions, I'll also create some boundary groups in which the boundaries will be assigned, and then they will be activated during the construction stages, and same thing will be done during the definition of various static loads onto the structure. This is how the construction sequence is laid down. At first construction stage, we'll begin the day 1 with the piers and abutments already in place with an age of 30 days. That means they have been cured for 30 days. And then this particular stage, CS1, will be of 21 days. We are giving 7 days for putting up the formwork and 14 days for setting off of the concrete because the segments are cast in situ. Then stage 2, the segments are activated with an age of 14 days, and they are cured for the next 14 days. So this stage 2 will be of duration 14 days. Then once the segments are cured and the concrete has gained its strength of characteristic strength at 28 days, in stage 3 it's just of 1 day duration, where we'll be applying post-tension tendons onto the structure. And final stage will be of 10,000 days, where the tendons will be first grouted and then superimposed dead loads will be applied onto the structure. And the reason we are having this stage as 10,000 days is we want to consider the long-term losses onto the structure, considering the creep and shrinkage. Then we'll quickly do the analysis and go to the results. So this is how our bridge looks like in the overall layout. It has 2 spans and 35 meter each, and then there's a very slender column underneath it, which is 10 meters in height. And this is the box section that we'll be modeling today. And this is a visual representation of the construction sequence. So stage 1, as I said, will start with the abutments and pier already in place. SG stands for structure group, BG stands for boundary group, and LG stands for load group. So the entire model can be divided into 3 parameters: structure, which comprises of all the elements and nodes; boundary group, which comprises of all the boundary conditions including supports and link elements; and load group, which comprises of all the loading conditions. So it's a complete 4D analysis where the 3 dimensions, that is the loading, boundaries and structures, are brought together against time. So in CS1 we'll assign some duration and activate certain boundary group, certain structure group with certain boundary groups and certain load groups in the first stage. Now then comes the next stage. We'll activate the structure group corresponding to span. Then come the next stage, we'll apply the post-tensioning strands, and the final stage we'll apply the superimposed dead load structure onto the structure. So basically, what all things we have activated in the first construction stage will be carried forward to the second construction stage, then it will be carried forward to third and fourth, and so on and so forth. And if you want to use some temporary boundary conditions, then you can apply them in a given construction stage and then take it out during the whenever they are like taken out from the real structure. Let's say for supporting this span, if you had several temporary supports, you can model them right here and then take them out once you are doing the once you have done the post engineering. But I have not gone into those details and try to keep things simple for the first time. So I'll come back to this slide once we start doing the construction staging, and let me start with the basic model. So this is how the Midas Civil window looks like. It's a new model I've opened, and I'll right click, go to the properties and material, click add to define the material concrete and ASTM, and I'll select 6000 psi grade concrete. I'll click apply. Then I can select steel material. I can go to ASTM standards and select A416 270 low relaxation strands and then click OK. So in this way I can define materials, and similarly I can go to sections. I can click add and go to precessed concrete section or PSC sections, where I can choose how many cells are there onto the sections. So I want to have a single cell or two cell. I can 3 cell, n cell, asymmetric sections, value type sections. So there are various parameters you can choose from. You can enter the name of the section and then the dimensions. But to save some time, what I'll do is import this section from the previous project that I have. So I'll click on import, and from a previous project where I've already used the similar section, I'll import it from there. This previous project file has two sections defined. One is box section, one is pier. I'll import both of them. I'll click OK, and now if I double click on the box section, you can see the dimensions as shown here, and I've used a section offset as center top. So if I click on display centroid, you can see the section offset at center top. The reason of choosing section offset as center top is for defining tendons. It becomes easier to control the geometry if you have a reference point at the top or the bottom, and especially when you're using some kind of tapered sections, the use of section offset makes all the more sense, because defining tendons with varying depth will become quite cumbersome. But here we are not dealing with tapered sections, but anyways, this is a fundamental approach for box girders, because most of the time when you are dealing with let's say balanced cantilever bridge, then you are most likely to use tapered box girders. I'll close this dialog box and also show you the pier sections. As you can see in this bitmap image right here, it's a solid round, and if I double click, you can see the dimensions as well. I'll click close. Now I'll start creating the model, and as you can see at the bottom in the status bar, the units are the imperial unit system. I'll switch them to SI unit system, since for this project I have the dimensions in kilonewtons and meter. Then I'll right click on the model view window and select nodes and select create nodes. And under create node, I'll create a node at the origin. Click apply. Then you can see the node created right here, and I'll use select single to select this node, and then right click, go to elements, and then go to extrude, and here I'll select the material as C6000, section as box girder, and translate them through equal distance in the x direction as 35 meters, and repeat it 2 times, and then I'll click apply. The moment you do that, you will see that the entire bridge created, and from here onwards I'll start modeling the supports and piers. Then I'll use single select tool and select the 3 nodes that are created. I'll right click, go to nodes, and translate them through equal distances, that is in z direction as -3 meters, because that is the depth of the box girder. Click apply. So you can see the nodes are created right at the bottom of the girder where actual bearing location is. And then I'll use single select and select the node number 5 and generate a pier underneath it. For this I'll right click element and go to extrude, and this time change the section shape to pier, and the distance will be 0 comma 0 comma minus 10 meters, and repeat it. Just I don't want to like replicate it, so I'll just say once and click apply. So as you can see, in no time the bridge geometry is ready. Now we'll go ahead and define the time dependent material properties. So I'll click close here, right click, go to properties and select time dependent material creep shrinkage. Then I'll click add, and here you can see you can enter a name. I'll use the name as C6000, and then I can select a code based on which I want to define this material behavior. So as you can see, we have CBFIP 1990, 1978, ACI, PCA, combined, ASHTO, and other European Indian standards. Along with this, we also have a user-defined feature which allows the engineer to have more control over the concrete material property for creep and shrinkage. And if you have a given set of data, you can go create your own curves for creep and shrinkage. But as we know, CBFIP code gives the best simulation or best results for creep and shrinkage for concrete material. I'll be using this code, and here I need to enter the characteristic compressive strength of the concrete. And to be honest with you, I have no idea how much C6000 or 6000 psi is equal to in kilonewton per meter square. So what I'll do is just quickly close this dialog box, go to the status bar, change the units from to kips and inch, then right click, back to properties, time dependent material creep and shrinkage, click add and enter the material name as C6000, code being CBFIP, and I definitely know it is 6 KSI, characteristic strength of this concrete at the age of 28 days, relative humidity being 70 days and 70%, and notational size of the member, I'll use any arbitrary value for the time being, let's say 12. This notational size is actually the volume to surface area ratio, and the definition can be found and the formulation can be found here. And this notational size is usually used for CBFIP. If you choose some different code, you will see volume to surface area ratio. Then you can select what type of cement you are using and what's the age of concrete at the beginning of shrinkage. And then if you click on show result, you'll see two curves. The first one is creep coefficient against time, and then shrinkage strain against time. Now what happens is when you define a construction stage with certain duration, and when the member is activated with a given stage, the program reads the corresponding creep coefficient and shrinkage strain values and then use it in determining the stresses or the secondary effects in the construction stage. So these curves are quite important to determine the behavior of your structure. Then you can click OK and close. After this, I'll right click again, go to properties and go to time dependent material compressive strength. Now here I'll define the gain in compressive strength, so I'll click add and enter the name. Let's say C6000. I'm using same name for different type of materials, and but you can completely feel free to go and define any name you want that suits you better. You can write compressive strength, you can write uh, anything except my name, of course. So You can generate the curves as per different codes as per CEBFIP, and here you can enter the mean compressive strength. This is a point you should pay attention on. Since we are using the code as CEBFIP, you can you need to enter mean compressive strength, which is not the characteristic compressive strength. FCK is the characteristic compressive strength. In that you need to add delta F, which is the standard deviation. So I'll enter that value. So 6 is my characteristic compressive strength plus 1.166, which is the standard deviation for concrete. Usually it is 8 MPa or 1.166 KSI, and then you click on redraw graph, and the program will show you the gain in compressive strength curve as per CBFIP. So the program knows that your characteristic strength is still 6 KSI, but your mean compressive strength will be 7.1666 KSI. Then I'll click OK and close. So once we have defined these curves, and you can see they are blue in color. This means that they have not yet been assigned to any material property. So I'll right click, go back to properties, and go to time dependent material link. Basically this is a link that through which we'll associate the creep and shrinkage curves that we defined, the gain in compressive curve that we defined, with the actual material that we are using. And then you just need to click add modify, and then so you can see the grade C6000 that you are using will follow this creep and shrinkage and this compressive strength gain curve. Then click close. Now if you remember, for creep and shrinkage we use the notational size for the time being is 12, but clearly our box girders and our pier have different notational sizes. So the program provides an option of auto calculation of these values. So you can go to properties, go to change element dependent material property, click on select all. So the program will select all the sections that are there, and check confirm that the selection is on auto calculate and the code is CBFIP. Then you click apply and close. So the program will calculate the notational size for each and every member that is there in the structure, and then replace this value for the computation of creep and shrinkage at the given point of time during the analysis. And for this purpose it was easy for us to compute the entire volume to surface area ratio and just use it for once, because it's a symmetric and uniform or prismatic section. But if it was a tapered section where the notational size or the volume to surface area ratio is varying, then you can see this feature has a clear advantage. And if you want to verify what is the actual notational size, you can right click and go to tables, and you'll see that the actual notational size for these members is 17.87 and 29.53. Click close here. And so we have defined the time dependent material effects. Now we'll move on to define the supports. So right click, go to boundaries, and then go to supports. So now we'll start defining the boundary group name as well and assigning the properties to them. So I'll click on this button with 3 dots, enter the name as, let's say, piers and abutments, and click add, then close. Basically I'll use just one boundary group to represent all the support conditions. The reason being, I'm activating all the boundary condition at the same time in the structure. If I was supposed to activate different boundary conditions at different time intervals, then I would need different boundary groups. So if you can, if I bring back that slide, so you can see that I'm activating boundary just in the first construction stage. After that there is no more boundary groups are activated. And Similarly, all the things that I'll be activating in one shot, in one construction stage, I'll be using, I'll be putting all those elements in one group. So I'll have one group for pier and abutment, which will have the pier element and the abutment nodes. Then I'll have a different structure group for span, because I will activate this in a different construction stage. And if you see the loading load groups, they are different. Like self weight is activated in the first stage, so it's different. I missed out a diaphragm load in construction stage 2, which will also fall in a different load group. Then in construction stage 3 we'll enter the post tensioning, so it will have a different load group, and similarly for superimposed dead loads. So number of groups depend upon how you want to, how and when you want to activate the loading boundary groups or structural elements in different construction stages. So I'll select that boundary group that I just defined. I'll have a fixed support at the base of the pier. So I'll restrain all the degrees of displacements and all the degrees of rotation, and select the node at the bottom of the pier and click apply. Then I'll select the nodes for the support or the bearing nodes, where I'll release all the rotational degrees of freedom, and it's an expansion bearing, so I'll release dx also, and just have dy and dz restrained, and click apply. And now I'll right click, go to property boundaries, and select rigid links. In rigid links, I'll be creating the master and slave node behavior throughout the structure, and I'll select the boundary group first. Then I'll select the master node as the node where the support is applied, and the slave node which is directly above it. It will be a rigid body connection, and I'll copy the links along y-axis, and the distance will be in meters. So what I'll do is change the distance from inch to meter very easily, and distance will be 2 at 35 meters, and then click apply. So you can see the program has created the rigid links right there. If I switch to a wireframe geometry, you can see it more clearly. So you can from here appreciate that the unit systems are no longer a limitation with this kind of software. You can switch the unit systems as many number of times you want, and there's nothing like you have to stick to a particular unit system for a given project and change everything based using a calculator manually, because the program will take care of it. Now I'll click close here and go on to define the structure groups as well. So I'll go to the group tab, and you can see the boundary group that you created is right here. I'll right click on the structure group tab. I'll click on new with 3 dots. Basically if you click new, you will just be able to define one structure, one group at a time. So I can define the group as like pier and abutment. Then I'll right click and then again click new, and then I can define the next group, which is span. So but if I click new with 3 dots, I can define multiple structure groups in the same time. So when you just need to add 1 or 2 here and there, you can just right click and select new. Now I'll go ahead and define the elements that will comprise the structure groups. So I'll select the span and click on the span group, drag and drop it over the screen, and if I double click, you will see the element selected. And since I'm activating the pier assembly and the abutments in first construction stage, so I'll select the nodes that are corresponding to piers and abutments and put them under the pier and abutment structure group. Now having done this, I'm ready to define the loading data onto the structure. So for this I'll create the load groups. So right click on the load group, click new with 3 dots, and enter the name as self weight SW. Then I'll enter STL for superimposed dead loads. then I'll enter diaphragms, then I'll enter PES for priestess or post tension, then click close. So I've got 4 load groups right here. Now I can go to load tab and select static load cases, and now here I'll enter the name of that. I'll define the load cases, self weight, and I can select the type of load case I want to have. I can select either based on the code specification that this load has to be a DC type or DW type, or if I want to see the effects of this kind of loading only during the construction stage and not in the post construction stage, then I can choose that type of load to be construction stage only. But for the time being, I'll stick to the standard specification. That is self weight as DC, STL will be for bearing surfaces, so DW, diaphragm, it can be DC, and then PS for pre-stress, and I'll select PS from here also, then click add, then I click close here. So I've defined all the load group, I've defined the load cases. Now I'll assign values to these load cases. So right click, go to loads and select self weight. Now I'll select the load case name, I'll select the load group name, and I'll select the factor in the given direction. So along z-axis, -1 is a multiplier for gravitational direction, and then I'll click add. This way I've defined the self weight. Then I'll right click, go to load and select nodal load for defining the diaphragm load. I'll select the load case name as diaphragm, load group name as diaphragm, and then I'll enter the value, and I have this value with me in kilonewton, so I'll change the units from kips to kilonewton, and this value is -850 kilonewton, and then I'll use single select the node on which I'm applying it and apply it vertically. Having done this, I'll right click again, go to go to loads, and there I'll select element beam load and select superimpose dead load as load case name and load group name, and I want to have a uniformly distributed load onto the structure. You can choose whether you want to apply that at an eccentricity or at the centroid location. If you check this option off, the loading will be applied at the offset location, which is where you have created your center section offset, which in this case it is the section top or the center top, and I'll enter the value as -12 kilonewton per meter, and then I'll go ahead and select the elements on which I want to apply it, and then click apply. Once we have applied the superimposed dead loads, now we are ready to define the tendon pieces load. So I'll click close here, and as you can see on your screens on this stage tab, we have the tendon definition. Basically you can locate the same under load, pre-stress loads, and then under tendon property, tendon profile, and then tendon pre-stress loads. So basically defining tendon has 3 steps involved. The first step is define a tendon property. I'll click on tendon property and click add. Here I'll enter the tendon name as web because I'm going to apply them in the web of the girders. Then I'll select the type of tendon I'm using. It can be pre-tension, post-tension, or external tendons. Since it's a post-tension structure, I'll go with internal post-tension. Material I'll select as A416 270 low relaxation as I defined, and then I'll select the total tendon area, which is from, if I click on that button with 3 dots, I can select the strand diameter, and I can enter the number of strands that make up this tendon, and then click OK. So you can see that the program has computed the nominal tendon area and added here. Then I can enter the duct diameter, which is 0.103 meters, and the relaxation coefficient I'll assign this as per CEB FIP and use the coefficient as 5%. Then you can see the ultimate and the yield strength of the tendon material are given here. The curvature friction factor, wobble friction factor to be accounted since it's post tension are given here. We are also considering anchorage slip at the two ends of about 6 millimeters, and we can consider either bonded or unbonded tendons. So I'll click OK. So we are going ahead with bonded tendons. Then the next step is defining the tendon profile. So if you place your cursor there, it will show you what the icon represents. So I'll define the tendon profile now. I'll click add, and here I'll enter the tendon name, that is T_L for the left web. I'll select the tendon property that I defined, and then I'll use single select tool and select the sections through which I want to apply the tendons. So basically I'm using this through these two members. I can select the input type as 3D, the curve as spline, and then if there happens to be number of tendons passing the same location or same profile, you can multiply the effect of a single tendon by checking on typical tendon and entering the number of tendons that follow the same profile. But right now, since we have defined all the strands into one tendon in the tendon property definition, so we will not be doing this here. Now we have reached a point where we need to enter the coordinates for this tendon, and for this you can, if I bring this dialog box right here, you can see we have a spreadsheet which has the tendon coordinates. Let me bring this right here. So what I'll do is I'll just select the coordinates that I have for the tendon. I'll hit Ctrl C, come to the program, and then click here once and hit Ctrl V. Once we have entered the coordinates, I'll fix the point where the curvature is changing, and then I'll tell the program these points are defined with respect to which coordinate. Basically I know that my elevations for the tendons are defined with respect to top of the section, and I can register this with the program also by clicking on the profile insertion point is the ith end of element number. Now I don't remember the element number, so I'll just click here, go to that element and click again there. It will enter the element number 1. Then I'll just click apply, and you can see the tendon created. I'll repeat the same thing for the right web, so I'll change the name from T_L to R, and I can either modify the parameters, the coordinates right here, or I can just delete the entire thing, copy from the spreadsheet and paste it right here, fix the points of change in curvature, and then click OK. So you can see the two tendons are defined in no time. If I turn on the solid view, you can see the tendons are neatly placed in the webs of the two webs. Now I'll move on to the third step, that is to define the tendon pre-stress. I'll click on this icon, select the load case name as PS, and select the load group name as PS, and then here I'll select the two tendons on which I want to apply this load. So I'll put them into the selected list, and I'll choose if I want to apply it as a stress or a force. I'll choose stress, and while stressing at both ends you can specify which end it was checked first, because that will affect the friction losses in the tendon. So I'm choosing first checking is at both ends, so this means they are checked simultaneously from the two ends, and I can enter the values. I have this value in MPa, which is Newton per millimeter square. So what I'll do is change the units to Newton and millimeters, and then go ahead and enter the value, which is 1330 MPa and 1330 MPa. So you can see different unit systems can be very easily used in the program. Now when we do the actual post tensioning in the site, you can decide whether the tendons are grouted in the same stage as you are post tensioning, or you want it to be grouted in the following construction stages. So here we'll enter one, that is grout the tendons uh, after the pre-stressing stage by these many number of stages. So this means if I activate the tendons or apply the tendon pre-stress load in stage 3, the grouting will be done in stage 4. If I enter the number here as 2, so this means if I post tension the tendons in stage 3, they will be grouted in stage 5. So you must get this thing correct. So I am grouting it in the next construction stage, so therefore I have entered grouting after one stage, and then click add, and then click close here. Now I have defined all the static loads onto the structure, and to save time and lay more emphasis on the construction stage analysis, I'll not be going through the live load definition in this model. Rather than that, I'll have some more things to show it to you during this session. So now I'll go ahead and define the construction sequence, and you will see that it is exactly the same way I laid it out on that slide. So I'll click here, select generate, and enter the construction stage name, which is CS, and I want to have 4 construction stage, 1 2 4 as suffix. I'll check on to save step stage results, and if any additional steps I've used, click OK. And now I'll go and customize or modify each and every construction stage. So I'll double click on it. I'll enter the duration as 21 days. I'll click on the element tab, select the group representing the pier and abutment, and I'll activate them with a stage of with an age of 30 days. This means when the day 1 the construction is starting, the pier and abutment are already in place and being cured for 30 days. Then you can come to the boundary tab, and you can select the boundary group. You can click add to activate this boundary, and come to load tab and select self weight. Thumb rule of Midas Civil construction stage analysis is self weight must always be activated at first step of first construction stage, and thereafter if you have some members being activated in the later construction stages, the program will automatically compute their self weight and add it when the elements are activated in the field. So do not try to simulate the self weight of some members in first construction stage through point loads, and then later on activate the span and activate the self weight. This will lead to incorrect results. So you should activate the self weight no matter what happens in the first stage, even though your elements are activated in the following steps. Then click apply here, and I'll move to the second construction stage, and this construction stage is for 14 days. So previous 21 out of those 21 days, 7 days were given for putting of the formwork and 14 days were given for pouring of the concrete. So in stage 2, when the span which are cast in situ are activated, they are actually 14 days old. So I'll activate them with an age of 14, and then no new boundary has to be added. And on load tab, I'll activate the diaphragm load onto the structure, then click apply. So now for the span is already 14 days old, and now this duration is 14 more. So by the time we come to construction stage 3, the span has gained is a required strength of 28 days, and then I can just make this stage of this duration as 1, and under loads activate the post tension or the pre-stress loads, and then click apply. And the final construction stage will be for 10,000 days, and I'll just activate the superimposed dead load onto this stage. And since I've mentioned that the grouting will be done in this following construction stage, this is a stage in which the program will automatically grout the tendons. And then I'll click OK and click close. Now since we are done with all the definition part, I can go to the analysis and select construction stage analysis control, where you can click on time dependent effect and see the time dependent effect controls that are there. You can choose whether you want to have creep and shrinkage at all. If you want to have just creep, just shrinkage, or both. You can control the iteration steps here. You can consider the tendon tension loss effects for creep and shrinkage. You can consider tendon tension loss effects for elastic shortening. You can consider variation in compressive strength. If you want the effect of uh, time dependent material and on elastic modulus to be carried forward to post construction stage, then you can certainly check this on and consider that as well. You can also consider the rebar confinement effect by checking this option. Right now I'll be sticking to this default, and then all the loading that you will apply in this construction stage model will be lumped together under CS dead load, that is construction stage dead loads. But if you want to extract a particular loading out of this lumped loading, you can choose that loading and put it under CS erection load, that is that will be that will fall into the category of bearing surface and uh, utilities. But right now what I'll do is put everything lumped together in the CS dead loads, and you can choose to consider the concurrent force effects in the during the uh, construction stage analysis, and you can also uh, choose to see the results for each and every part of composite sections. But we are not using composite sections here, so this will not affect our analysis. And you can check on consider initial tangent displacement for erected structures. Basically then the program will able to give you the camber deformation, it will be able to give you the cumulative deformation, and it will also give you the deformation due to the loading that is activated in that particular step. And I'll quickly go through these results. Then I'll click OK here, and as you can see, there is just the span length is 35 meters. So the results will be given at 5 different points: I, J, half, 1/4 and 3/4 of the length. And certainly that will not be acceptable because the results will actually be at quite far intervals. So what I'll do is select the members, and do pay attention to this step, as this is the beauty of the software. I'll select these members after defining everything that is applied, and then divide this into, let's say, 7 pieces, and click apply. When I've done that, and if I go back to the groups, you'll see that the group has already been updated. That is with the divided elements, the number is updated to 14. If you come here and see the loading value, if I right click and display on the screen, it has also been divided and distributed throughout the length. If you see the tendon profiles, if I right click and go to properties, you can see the number of assigned elements have been automatically updated. So unlike other softwares which suffer from these kinds of drawback during construction stage analysis, or once they have defined the groups and loadings and other parameters, and they make any changes, they have to go back, keep a record of all the changes, and update the groups one by one. But the program is intelligent enough and takes care of these kinds of changes. Let me undisplay tangents and display the loadings, and now we are good to perform analysis. I'll click perform analysis and save this with some name, and click save. And the analysis has been completed, and as you can see, it just took about like 2.1 seconds. very simple analysis, simple model, and I can cycle through the construction sequence by clicking on this text field and select CS1, and I can choose to display the boundary conditions. So I can choose to display supports. So you can see the supports activated. It is an exact replica of what you saw in the slides. Second step, the span is activated, and third step, let me display the tendon profiles. Miscellaneous tendon profile name, tendon profile points. You can see the tendons coming into picture. And the fourth stage, you can see the loading coming onto the structure. Let me display it onto the screen. You can come to loads and select all the element beam loads to be displayed. So in this way you can see the construction sequence, how it has been laid down. And now what I'll do is switch to, I'll just clear this display. Let me just display this. Okay, so now let me cycle through some results real quick. Coming to post CS, I'll just first verify whether my loading data is correct or not. So right click, go to reactions, reaction forces, select sulfate, and then click on this button to generate the table real quick for sulfate. And now if you put together all the structure sulfate, it should match this value. Let me scale it down to kilonewtons, or better if I scale it down to kips. So you can do the summation by multiplying the cross-section area and the material density. You can get this force and just verify that the loading is correct or not. Then I'll right click, go to deformation, displacement contours, and then just because of sulfate, let me see how much is the deformation of the structure. You can see it's about 7 millimeters. Let me change it to inches, and you can see it's about like 0.23 inch, 0.29, approximately 0.3 inches. So basically there's no highly undeformed shape or abnormal deformation. So this means all the nodes and members are properly connected. Let me move on to the forces and come to beam diagrams. And here, just because of sulfate, let us see how much is the bending moment value. And as you can see, this foot kips, you'll see this value. So I mean, and this graph also looks, the diagram also looks pretty correct, because it has interior support, and this is due to the sulfate. You can expect this kind of diagram. Hence our modeling is correct. Now I'll move on to construction stage results and view the results one by one. So I'll come to the first construction stage, which has just pier in it. Let me see from second construction stage. You can see the results for CS dead loads that will sum all the dead loads onto the structure, which is primarily just the sulfate for now. And you can notice the values that are shown here. And once I go to CS summation and click apply, you can see the values are same because the elements are just activated on the first step. But if I come to the last step, that means when the age is 28 days, you can see the variation in the bending moment value, and this is where the time dependent effects kicks in, because if I come to first step, the elements are just activated, so there's just sulfate acting. Now due to the time dependent effect, you can see the values are changed. Now coming to this third construction stage, where we bring in the tendons, and you can see the bending moment has reduced as expected. And then if I click apply on the last step, you can see the bending moment slightly changing. And the last construction step, last construction stage, first step, is where you have added the superimposed load onto the structure. You can see the bending moment, and when you come to the last step and click apply, you'll see the increase in the bending moment because of the time dependent effects kicking in. Now similarly, you can see the results for each and every construction stage for deformations also. Displacement contours, you can come to displacement contours and go to second construction stage, and due to summation loading, You can see the displacement that is occurring at different construction stage, at first step, last step. Then you come to third construction stage. You can see the time dependent effect playing its role. With the post-tension tendons coming in, the displacement is reduced to a certain bit. But when you come to the final construction stage and final step, click apply, you'll see that this is the overall deformation that is occurring in like 10,000 days. I mean 10,037 days. This is the total duration of construction stages. And you can choose to see these are the camber values that you are looking at. You can see the current step displacement. This means the displacement that will occur due to all the loads that are activated during this stage only. If you want to see the real displacement, that is the summation or the cumulative displacement, you can click apply, and this is the cumulative displacement of the structure. So the program is able to generate all these different results for construction staging for deformations and forces, and same thing can be done for stresses also. You can choose beam stress pre-stressed concrete section. You can select 10 different locations along the outer fiber and choose, let's say, for top fiber for sigma xx or sigma xx summation. You can check off the deformation and see the stress values at the top position, at the bottom fiber position. So you can see the reverse graphs. You can use solid fill. So for top fiber and bottom fiber, you can see the values, and um, due to time limitations, I'll not be going into the design features of Midas Civil for pre-stressed concrete sections. We will be taking up that up as a future topic. But right now I'll be sticking to these results. So all these results are, as I mentioned, can be extracted in spreadsheet also. So you can right click, go to, let's say, forces, beam diagrams. You can click on this button with 3 dots. You can select which construction stage, which step you want to see, and then click apply. The program will generate those results for you. Also, you can see the tendon tension loss effects. You can come to post CS now, and under results you can go to result tables and go to tendon and select tendon loss. And here you can select the tendon strand and which construction stage you want to see the result. Let's say final construction stage, when all the losses have occurred. Click apply and you will see the values for tendon stress losses. Let me change it to kips and inch so you can have a better idea about the values that are there and the losses that are occurring. So you can see the stresses after immediate losses. If you remember, I applied the values in MPa, so let it be Newton and millimeter square. So I applied 1330 MPa since it's post-tension strands. So due to immediate friction losses, immediate relaxation loss and anchorage slip, you will get this kinds of losses. Then there is elastic deformation. This is the ratio between the stress loss after elastic loss and the intermediate loss. The creep and shrinkage losses that are occurring during the long term, the relaxation losses that are occurring during the long term, and this is the ratio of stresses after all losses and immediate losses. So you can generate these kinds of table very easily. It can be generated for stresses as well as for forces. It doesn't matter if you apply these stresses as stress values or force values. You can still extract the result for either of the two. So let's say kilonewton, you'll see this kind of loss values. Same thing can be animated in a tabular format. You can go to results and select tendon tension loss graph, and you can choose the tendon, let's say tendon for the right web, and then click animate. You will see the steps are changing and the program is showing you the tendon losses in different construction stage, and you can read these values and make out whether these graphs makes sense or not, and verify your tendon profile. So this was all I wanted to share with you in the webinar of box girders with construction stage analysis. But before I wrap up this session, let me quickly share one more aspect of Midas Civil here. Let me just go to the second file. Yeah. So if I summarize all the modeling steps here, so we started by defining materials in section, then we create the structural model by creating nodes and elements and providing boundary condition. Then we define structure groups, boundary groups, load input, and then apply tendons and did the pre-stressing or post-tensioning. Then we define construction stages, and the time-dependent material properties can be defined at the end or at the beginning, and then we perform the analysis. So you can see that this is a simplified approach to construction stage analysis, and this can be further simplified by the use of wizards that are there in the software. So if you see here, all these steps can be summarized by Midas Civil wizards, where you can just define the material and section property, and the wizard will take care of the entire definition of structural model, defining groups, creating construction sequence, and entering tendons and everything will be done here. All you need to do is then define the time dependent material link and then perform the analysis. And to show you how simple it is, I'll go into the program itself, open a new file here, and I'll go to model structure wizard, and then there are several different wizards for segmental construction. Based on the type of construction methodology, you can pick and choose the ones which are favorable to your project. You can use either incremental launching, balanced cantilever bridge, or movable scaffolding system, or fully shored method of construction. Since what we did today is very similar to span by span construction, so I'll show you how you can generate a bridge in no time using MSS wizard. So what you can do is this wizard has 3 tabs: model, section, tendon. On model tab, you can specify the longitudinal profile, like what's the bridge material. So I'll just quickly define, or rather I will just import it from the previous model, the material property that I'll use. Click close here. So this is the material. Then you can define what is the span length you want to have. I will have 4 spans, 1968, and 2 spans of 2364, and then 1 span of 1968. So they are unequal spans, and right now I'm going with the default values. If you want to consider radius of curvature, you can include that. You can specify along the longitudinal axis where you want to have your fixed support, so you can specify that location from the origin and specify which span it is, and then how many segments you want to divide in a span. So you can choose that number here. I'm using 20. Then where you have the cold joint, basically when you have the span by span construction, then you construct one span and then create some portion of the second span, so that the beam is never simply supported, it has a overhang there, and then you have the second span attaching at this location. So this particular location becomes your cold joint. So you can specify what is the distance of this cold joint from the previous support, and then you can specify the anchorage. So when you have the tendons which are running through the webs, you can specify how much length should be given for overlapping and anchorage, and you can specify or where those tendons should be anchored, how deep inside the previous span, and you can specify what is your diaphragm thickness at the supports. Then what should be your stage duration, and what should be the initial member age, and what should be the weight of your movable scaffolding system. So basically, initial member age is how many days you want to give it for setting of the concrete and before you remove the formwork. So that is the age here. Since it's a segment by segment construction for the span, we are giving it like 5 days of curing before we remove the formwork from there. So when the span will be activated, it will be a 5-day age concrete, and then we'll continue the construction, and then they will gain on age. So this is just for demo purpose. We are just starting with some values here. I'll move on to the section tab. Here you can define it's a 1 cell or 2 cell section. You can define the different sections for center, for joint, and for diaphragm. And then I'll come to the tendon tab, and here you can define the tenant layout. You can select from uh, different type of layouts and control their variation. You can have it in 1 layer or 2 layer. Only thing you need to do is enter these the parameters just by looking at the bitmap image. I'll just define the tenant property here real quick. Let's say web, it is same as what we just defined. General tenant area, I'll just use the same as previous. The duct diameter, let's say what was about 10 centimeters, so this will be about 4 inch. Then relaxation coefficient and all the other parameters remaining as default. I'll click OK and click close. So I've defined the tenant property, and I'll be grouting the tenants every one step. That means not at the precessing step but in the following stage. I'll be grouting it, and I've given it the 2-layer formation and the distance. And then when I click OK, you will see the program has generated this model for you. If I come to Works tab, you'll see all the data there. And then let me display all the support conditions and cycle through the construction sequence. So I'll come to first stage, and let me zoom out a bit here so that you can see the full model being created, and fix the zoom here. So you can see at first step, this is the roller end, and this is a fixed support, and this is the distance given for cold joint, I mean the overhang. Then second step, we'll have the next span erected, and this will still be the fixed support, and this will be the roller end. Then third step, you'll change the support condition from fixed to roller and make the other end as fixed. Then you come to fourth stage, you'll have this end as fixed and the other end as roller. And then you have the final construction stage where you can add your superimposed dead loads and tenant precesses. And if I just display the tenant profiles here, you can see 48 tenants are generated. I can choose to click display, and you can see them onto the screen. They've been applied throughout the construction sequence. Let me undisplay it. So very basic, similar, simple geometry, span by span construction. You can see it can be done in no time in the software. Just needs little customization here and there. You can see all the boundary conditions, structure group and load groups are automatically created. So the program saves a lot of time on the iterative steps that you have to perform, and now you can still go in and modify your set of or rather I should say you can customize the bridge as per your real project and go ahead and do the analysis. So this is where the software's power is utilized, and you can see in no time you can generate different kind of segmental bridges and consider all the construction stage analysis and time dependent effects. So if you have any questions or concerns, you can ask me right away, or you can write me an email at my contact detail, which I'll be putting up on the screen shortly right here. So you can directly give me a call or write an email for your comments and suggestions, and I'll be more than happy to respond to them.